Hello and welcome back. So what I want to talk to you about today is switch mode power supplies and the noise they generate. And for that I've got this little supply here which I've been working on lately. Basically this is a booster supply that has a voltage tripler stage on top of it. And it's taking 12 volts and generating about 78, and right now the load is set so that there's 7 milliamps, well, almost 8, coming out of it. So the supply seems to be stable. But is it? Let's just have a look at it. And for that I'll be using this low noise connection. So I don't have my long ground lead, I just have this small little spring. So if we look at the output, we can see that it's not perfectly stable. Now, granted there's only 20 millivolts per division, so this thing is quite small, but we can still see that there is some sort of oscillation in it. And this, as you can see from the cursors, is around 15 kilohertz or something like that. But let's just zoom in, see exactly what else we got in here. So we can see this triangle wave going on. And this is at a much higher frequency. So this is right now going at 1.5 megahertz, the switching frequency. So this is the rate at which the power supply is switching. And now if we zoom in even more, we can see that we have even higher frequency noise. So we've got this little ripple here on top, we've got this major spike here, so there's a lot going on. And when analyzing switch mode power supply noise and ripple, it's important to understand where these are coming from, since there's multiple types of noise and all need to be addressed. So if you're curious about where these things are coming from, how we can fix them and how we can simulate them, then keep watching. So I would like to start this electronics tutorial off by saying that this is the power supply that I'm actually using. So this is tiny little IC, and the reason why I chose this is because it's so small and so compact. So most of the things needed to build a power supply, like oscillator, reference, compensation, everything is integrated. Even the switch is inside. So if you want to build a boost circuit with this thing, you just need a handful of components. But there's a drawback, of course. If we go to the manufacturer's website, so the chip is made by Diodes, we can see that the manufacturer does not provide a SPICE model for this IC or for any other booster that they're making. So now we have a problem. How do we simulate this? Well, one way would be to try to create a model based on the block diagram, and that could be reasonably accurate, but it implies a ton of work. On the other hand, you can do the next best thing, and that is look for a power supply made by linear technology that's basically the same as the one that you're using. So what I found was this chip, so the LT3467, that also has integrated switch and everything else, and you can also build a very tiny, very compact supply with it. The only difference being that it runs at a slightly different frequency, and it has this external soft start capacitor. But other than that, if we look at its block diagram, it's almost identical to the chip that I'm using in real life. So with that being said, let's start simulating. So basically, this is the circuit that I've built, other than the IC, of course. So I'm powering it from 12 volts. I got a 47 microhenry inductor, 5 diodes, 5 capacitors built into this voltage tripler arrangement. Then I got my feedback resistors and of course an output load. Now to get the supply to reach steady state much faster, I also included this initial condition statement so that the output will stabilize much faster. So if we run this thing and we look at the output, we can see that it started from 60 volts because of the initial conditions statement, and then it stabilizes somewhere between 78 and 76 volts. So the difference from this to my real supply is coming from the tolerances in the feedback resistors and the internal reference tolerance. But that's not really why we're simulating today anyway. So if we look at the output, we can see that it's not perfectly stable. Actually, it's quite similar to what we got in our real measurement. Now the ripple size and type is not completely the same, of course, but we're getting the same phenomenon nevertheless. So how do you fix this? Well, if we go back to the datasheet, so not this one, the linear technology one, in their applications information section, they tell us about how you should properly compensate a switch mode power supply. In this case, the Boost power supply. And they give you a lot of formulas and equations and some good information about how this should be done. Now, the problem with this is that we're not really using this IC, we're using the other one. And there are a few parameters that we don't know, and we can't really know, is the internal gain of the amplifier in the switching supply, and also the internal compensation components. So you can make some proper loop analysis simulations if you have the right model, but in our case we don't, so we won't bother with that. The only thing that we can do is at least find out how we could try to fix our problem. Basically, the stability of the system can be influenced by the output capacitor and its ESR, and an extra feed-forward capacitor that can improve loop response. So we can try to play around with that. So for that, I added the ESR to all the capacitors, 8 milliohms in this case. So this is the typical ESR for this sort of 1 microfarad ceramic capacitor, and then added this compensation capacitor with various values. So we'll first be simulating with 1 picofarad, that would work like there's nothing there, and then 2 more values, see exactly what happens. So we can already see that you can't just put any value, so there is a case in which it will go horribly wrong. In our case, it was the time when we added 470 picofarads. But if we look at the other two traces, now it's not completely obvious because of the way they're overlapping, but the blue trace has a bit less ripple than the green trace. And in our case, the blue line is the one in which we added the 100 picofarad capacitor. So adding a capacitor in parallel with the upper feedback resistor should help. But does it? Let's just make sure. So this was the measurement when no capacitor was added. This is the measurement in which I added 120 picofarads. I didn't have a 100 picofarad capacitor. So the ripple did decrease. We went from an 80 millivolt ripple down to a 50 millivolt ripple. And if I add 470 picofarads, then we get this nice oscillation. So just like in the simulation, too much capacitance will make things worse. So when analyzing switching supplies, if you get ripple that has a frequency lower than the switching frequency, most likely it's coming from the system's stability. And you can correct this by working on its compensation. So time to move on. The next thing that we saw was that if we zoom in even more into the output voltage, we can see that we are getting a noise at the frequency of the switching supply. So if we quickly resimulate the circuit and add this 120 picofarad capacitor, and we look at the output in a bit more detail, we will see that we also get this nice triangle shape. So just like the one in the real measurement, only we're missing some of these higher frequency spikes. But we can get a better idea of where it's coming from, so its amplitude, by varying the various parameters in the power supply. So the first thing that I've done is add some proper models for the diodes. So no longer working with some generic LTspice models, but rather proper models coming from their respective manufacturers. Now if we simulate, the output mostly looks like it did before, it's just that it's a bit more smooth. So here the proper diode models did help a bit. Now this is not where this ripple is coming from. Now the next thing that we can try to play with are the capacitor's parameters. So right now our ripple is at about 30 millivolts. Now if we play with the output capacitor, we can see that based on its value, the ripple will be smaller or larger. So this huge ripple we get when we put a very small output capacitor, so only 100 nanofarads. So for all three of the output capacitors, I put 100 nanofarads and got this thing. But if we put a bit larger capacitors, we can see that the ripple will reduce the higher the capacity is. So basically, most of this triangle shape ripple is coming from the capacity of the output capacitor. And the reason for its shape is coming from what the capacitor is doing in the circuit. So on the rising edge, the capacitor is being charged by the inductor, and on the falling edge, the capacitor is supplying the output load. Now you may notice that there is a small drop in between. So when going from a load to a generator and back to a load, there's this straight drops on the output voltage. And these are coming from the capacitor's ESR. So right now we're simulating with 8 milliohms, but let's just try some different values. So first of all, I'll just put back the 1 microfarad capacitors, and let's play around with some ESR values. So let's try 0.1 milliohms, 10 milliohms, and let's use a very bad capacitor, 50 milliohms. So now if we look into the results, we can see that the green line, in which we didn't have any ESR, so very small values, we have a almost perfect sawtooth, so it goes from falling to rising edge directly. When we added 10 milliohms, we had a bit of a drop, and with 50 milliohms, the drop is even higher. So in this sawtooth shape ripple, the curved part is coming from the capacitor's capacity, and the more abrupt part is coming from the capacitor's ESR. So what else can we do to influence this ripple? So I just corrected the ESR first. So one thing that we observed is that part of this ripple is coming from the capacitor charging and discharging. And this of course is influenced by how much current is coming out of the power supply. So its load. So if we play around with the load a bit, add a small load and a larger load, and we look at how the output looks this time, so without varying any other of the parameters, we can see that the ripple is larger if the current output is larger, and it's smaller in the other case. So let's just check this thing in reality. This is basically how the output looks when we only draw 8 milliamps from the supply, and this is the same thing with 11 milliamps. So first of all, we can confirm that part of the ripple is coming from the load current. We get this sharp transition coming from the ESR, and we can try to correct things, or at least make them better, by adding some extra output capacitors. So if we add an extra 1 microfarad capacitor on the output, we get something like this. So in this measurement, I'm still taking 11 milliamps from the power supply, but the difference between this one and this one, so going from 60 millivolts of ripple to 30 millivolts, is the added output capacity. Now the high frequency noise looks the same. Adding this capacitor just corrected this lower frequency noise. Now it's important to mention here that adding extra output capacitors can have an influence on the system's stability. The output capacitance and its ESR are part of the stability calculations of a power supply. So especially after adding large capacitors to the output of a power supply, just make sure to check that the supply is still stable. So now it's time to analyze the high frequency noise. And you can see that my measurement doesn't really look like my simulation. So in my simulation I have very nice waveforms, whereas in the measurement I have all these little glitches. So what's still missing? Well, any capacitor has 3 main elements. It has capacity, resistance, and inductance. So I've covered in a different video how to properly model capacitors, but in a simple way we can model my capacitors by adding an extra 470 picohenry of inductance. Now at this point you might be wondering, where am I getting all these parasitics values from? Well, I went to this website, so to the TDK's capacitor model page, and here I just took a generic component type and went with the simple model PDFs. So what is in these documents? Basically you'll get something like this. So they are covering an entire series based on its type, voltage, and case size, and they're giving you all the parameters for the 4 major components that describe the capacitor's parasitics. And you get all these data laid out very nicely. So one of the interesting things that we will observe here is that the inductance, so the equivalent series inductance of the capacitor, doesn't really change. So it's the same for the 1 nanofarad capacitor as it is for the 22 microfarad capacitor. So this inductance is case size dependent. And of course, if we go to the table for a different case size, we get a different inductance value. So of course, this is just a simplified model. The real inductance is different a bit, but for now, this will be good enough for our models. And also adding my extra 1 microfarad output capacitor. So of course I could be using much more complex models, but this is just to show how the parasitics are influencing the results. So you can already see that simulation is running much slower. We're getting all sorts of these quite high voltage oscillations. And this time, if we zoom into the output waveform, we can see something that resembles our measured waveform much more closely. So we can see that we're getting, both in the simulation and in the real measurement, two distinct spikes. So one is happening when the switch turns off and it starts charging the output capacitor, and the other is happening when the switch turns on and the output capacitor starts discharging into the load. So we can see that the last missing piece of noise is coming from the parasitic inductance. And we don't just have inductance from the capacitors and from components in general, we also have inductance from the layout. So this is the board that I'm currently making measurements on. So I got my input voltage, the output voltage, the switch IC, the inductor, part of the capacitors, the diodes, and some more capacitors. And I mean, it's a tiny little board. It's not the best layout, but it serves the purpose. So we can see that we have certain lengths of trace. So if I take my measurement tool and look from, let's say, here to here, we have 4.5 millimeters between these two components. And roughly most of the traces have around 5 millimeters of length. So what's the inductance of this trace? Well, if we go to Google and look for a random trace inductance calculator, we can either use the massive formula to calculate this, or we can use the website. So we had a 4.5 millimeter trace. Its width was about, let's say, 2 millimeters. The copper thickness is 35 micrometers, I think. This is just to get an idea. And if we calculate this, we get 2.4 nanohenries of inductance, which is way more than the 470 picohenry that the capacitors have as parasitic inductance. So one of the major contributors to the output noise will be the inductance of the traces. So if your layout is all spread out like this, you will have bigger problems than if you manage to get it much more compact and get the traces much shorter. So right now, the simulation that we are performing in LTspice is resembling our measurement quite well. But if we look in a bit more detail, we see that the simulation is making some more predictions about the noise that we can't really see in the measurement. So we can see that we have this glitch here, but in our simulation, we also have this very high frequency noise going on. So this thing is at around 5 gigahertz. And in our measurement, that area is perfectly clean. So am I doing something wrong? Why can't I see this thing in my measurement? Now at this point I find it critical to point out that the measurement your oscilloscope is making highly depends on the quality of your oscilloscope, your measurement probe, and how you set up your oscilloscope. I mean, you can have the best oscilloscope in the world, but if you don't know how to use it, then you're not going to make very good measurements with it. So right now, this is the noise measurement that we were previously looking at. And this is the same noise measurement. So what's the difference between this and this? I mean, it's the same measurement. I haven't moved my oscilloscope probe. Basically, what I'm playing around with is the bandwidth of the oscilloscope. Now this oscilloscope has a 70 MHz bandwidth. That means that signals that are at 70 MHz will be attenuated by about 3 decibels. Everything above that will be attenuated by more. And this option that I'm playing with doesn't just take the oscilloscope's built-in 70 MHz bandwidth limitation, it lowers it to 20 MHz. Now this is useful when you're looking at very noisy signals. But in this case, when we are actually looking at very high frequency signals, then we don't need this, so we should be turning it off. And if we do this and we start looking into our signal, we can see the high noise frequency content a bit better. So we can see that we have a lot of oscillation going on, and if we try to measure this using our cursors, we find out that this noise is running at 100 MHz, or maybe even more. The oscilloscope is not capable of measuring it. So if you do have an oscilloscope that is capable of measuring into the gigahertz range, then you will see this noise very, very clearly. But if not, then you either have to rely on a very good simulation, or just hope that there is no such extremely high noise going on in your circuit. So now that we know that our supply is noisy, and we can have confidence in our simulation's ability to reproduce it accurately, let's see what can be done about this. Well, you may remember that when we added the extra 1 microfarad capacitor, the high frequency noise didn't really change. So this was the noise without the 1 microfarad capacitor, this was the noise with the 1 microfarad capacitor. And you can see that most of the high frequency noise was rather untouched. So why do you think that is? Well, if we analyze our capacitor's impedance, and we rescale a bit things to make them a bit more clear, we can see that the 1 microfarad capacitor acts like a capacitor up until 6 MHz. Afterwards, the impedance starts to rise and it behaves like an inductor. So at lower frequencies, adding a 1 microfarad capacitor will help. It will reduce the noise, reduce the ripple, everything will be fine. At high frequencies, on the other hand, the 1 microfarad capacitor won't be doing much, since it will be acting like an inductor. And this is why you may have noticed that power supplies and all sorts of other circuits don't just have one capacitor on the output, but they have many capacitors on the output, all being of different value. So if we think about a different capacitor, let's say 1 nanofarad capacitor, same series inductance, maybe a bit more series resistance, and we analyze this thing and compare it to our first capacitor, we can see that the 1 nanofarad capacitor will be acting like a capacitor for a wider frequency range, although its impedance will be higher than that of the 1 microfarad capacitor, but even above the 6 MHz point, it will still be acting like a capacitor, and there will be a certain frequency at which it will have a lower impedance. So one of the things you can try, when trying to reduce the noise of your switching supply, is add some low value capacitors. So if we add the 1 nanofarad capacitor into our circuit, and compare to the circuit without the 1 nanofarad capacitor, we can see that the simulation is going very slowly since it has to calculate two very complicated circuits. But other than that, if we zoom into our measurement this time, we can see that our noise amplitude has reduced substantially, but it changed frequency. So what the extra capacitor is doing is absorbing this very high value spike and then releasing it in a slower rate. So basically, our peak-to-peak value has reduced, although now we have different oscillation going on. And this is what we also see in practice. So this was my initial measurement with a 20 MHz bandwidth limitation, of course. And this is what happens if I add the 1 nanofarad capacitor that I'm simulating with. We can see that the spike is being absorbed and then released in the form of this oscillation. Now if I try with a 10 nanofarad capacitor, the amplitude is even smaller and the oscillation even bigger. So it might first seem that adding this capacitor made the noise worse, but actually it was reduced, as can be seen in the simulation. It's just that the measurement was not able to pick up the full noise that was initially there. So one thing that you can do is add such extra lower value capacitors. Now on the other hand, another thing that is important to remember is that usually your load will not be directly connected to the output of the supply. There will be a certain length of trace and then your load will be somewhere else on the board. And if we remember our talk about parasitics, we can consider the length of wire going to the load as having a bit of resistance and a bit of inductance. So let's say about 5 nanohenry and 100 milliohms of resistance. So this is a very thin wire and it has a bit of inductance. Now it's common practice for every sort of load that you have on your board to have a local decoupling capacitor. So if we simply take this 10 nanofarad capacitor and also add it as a decoupling capacitor close to your actual load, then we can see an interesting phenomenon going on. So this is how the noise looks like at the output of the supply when an extra 10 nanofarad capacitor is added, and this is what it will look like at the actual load. So when you also use a decoupling capacitor and you rely on your trace parasitics, you can see that the very high frequency content has been filtered out and you're only left with a small oscillation. So this is why it's common when performing noise measurements to use the 20 MHz bandwidth limitation, since your load will most probably not really see this high frequency noise. It will be filtered out by the trace and local decoupling capacitors. Now the amplitude of the lower frequency noise has remained unchanged if the decoupling capacitor is small. If this would be a bigger capacitor, say another 1 microfarad capacitor, then the output would look completely different. So to conclude this electronics tutorial on switch mode power supply noise and debugging, we can say that there is an easy and expensive way to filter out noise that uses tons of filters and stabilizers and whatever else you can think of. Now that will work, of course, but there's also a smart and cheap way of doing things. So you need to understand exactly where all the noise is coming from and what are the best and simplest ways of dealing with it. So all in all, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and hope to see you next time. Bye bye.